Alright, time for another draftphysics.com, debatephysics.com video presentation. So again, still on the subject of thermodynamics, this will be part 2. Okay, playing the Jim Al-Kahari video that was called something. Who knows? Matter and Energy, I don't know. I don't remember what the actual original title was. Anyway, and I believe I will begin with some observations. Yes, so we'll save that for later. Playing the video, actually. Um, thinking about hydrogen and its fact that it's buoyant tells you something, about the fact that it floats above all the other atoms in the pressurized atmosphere, and it's got to be doing that for a reason, and the reason's got to be that the atom itself takes up more space. Okay, that the electron and the proton are, let's say, pretty far away from each other, and therefore the dimensions of space that the hydrogen atom occupies is large. And it seems a reasonable explanation for why hydrogen's buoyant. And the argument is that the neutron, okay, is basically just the same thing. And the argument would be is that it's been the space that the hydrogen atom is taking up is much smaller, and so it's more compact and more compressed, and so it's in a state that makes it distinctly different in terms of its behavior. And so we've called it two different things, but it's really just hydrogen at a different energy level, you could argue. Okay. One hydrogen is consuming more energy than the other hydrogen. Which is debatable. But the thing about neutrons, the thing that is an observation, let me just make this bigger and call it a proton. Okay. And so you have a proton and an electron, and I really shouldn't draw them different sizes because technically they're seeing each other and the charge is the same between them, so they really have to be the same size. So I don't know why I'm using this pen. Yeah, it's the wrong pen. So I solved the problem by using color. Yay! All right. So electron and the proton. Now, obviously, they say stuff about some kind of neutrino or anti-neutrino as part of this. There's absolutely no need for any of that kind of nonsense. So a neutron is basically a proton and electron close together, and what you really can observe is that they form, okay, a straight line. So you could sort of understand that that's where you change this idea of direction and you start creating a concept of direction. And the idea would be is that, well, if you apply energy this way, you're likely to spin it. Okay, so you can't really apply energy from up or down because you're going to end up just turning it. Where if you apply energy in this direction or you apply energy in this direction, you will move the object. So this is where you start just getting to the simple dynamics of how it functions. So the sun is under extreme pressure because a bunch of elements are being given momentum all from all directions. All right. And creating extreme pressure. So you can understand that the engine is really converting hydrogen into neutrons. I mean, that's the real key ingredient, is the creation of the neutrons. And that's part of the synthesis of when you combine two hydrogen atoms or three to make a helium nucleus. That what you're really doing is expelling a neutron in that process, and that's the that's the energy you're getting. So you're creating something quiet, the helium nucleus, and you're expelling with some energy the mobile bit that can move in a direction because of its now linear shape. It now has a shape. It's got a shape this way. All right, that's very different from its shape in the other dimension. All right, so I had some other observations on other subjects, but I guess I'll just throw in one quick one. Just because I'm not going to be able to make separate videos. So, throwing something else in, on the kinetic energy thing. The Mythbusters did an experiment where, they crashed two 50-mile-an-hour cars into each other. And not only did they not get the fact that, well, these are basically two springs, so obviously you're going to crush one spring over here and you're going to crush one spring over here. So in some sense, yes, it duplicates a 50-mile-an-hour crash, okay? That, each individual car is going to experience the same thing as a 50-mile-an-hour crash into a brick wall, and there's not going to be any experience of the 100. But obviously, if you said these were solid objects and you crushed something in between the two 50s, that would feel like 100 miles an hour, which I think was the real point being made. I mean, the real issue. So not only did they not get that right, but in thinking about it, the real key is, what's the distinction then? So, I mean, in a sense, they were saying crashing into a brick wall is the same as at 50 miles an hour as crashing into something going 50 miles an hour. They were essentially saying those are two circumstances that would feel the same. And what they were missing was this crash will happen in half the time. Okay, the two 50s, the crash, the crushing, the expenditure of the energy will be in 1/2 the time. So the G forces will be double. So you have 2x the G forces. So in the 50-mile-an-hour crash with the brick wall, you experience a G force of, say, 50, and in the crash with another 50-mile-an-hour car, you're going to experience G forces that are 100. Okay. So it's because it's going to happen twice as fast. Your deceleration will happen twice as fast. It'll be the same crushing power, the same stopping power. It's just being applied faster. And that relates to this whole stupid argument about kinetic energy, right? Because it's all just about the fact that there's this illusion, that something happening faster means it has more energy. And it's not that it has more energy. It's just that you're applying the energy faster over a quicker period of time, and so you're creating more disruption in most of the things we know of. Most of the materials we interact with are speed sensitive. If I hit this with a high vibrating, high velocity, it'll break. It doesn't have to be a lot of energy. It just has to be at a high velocity, and it can't dissipate the energy. The energy can't travel through the ceramic material quickly enough, and so too much energy gets concentrated in too small an area, it gets too hot essentially, and it breaks. Fractures. Okay, and a lot of things do that. And so that's the real, so you get this slight indication, in life experience that fast things have more energy, but they don't have more energy. They just distribute their energy over a smaller and smaller period of time, which means essentially this idea of G forces. They're imposing a G force difference, okay, which isn't more energy. It's just that it's happening too quick for the thing to absorb it. So we can absorb a certain amount. An egg can absorb a certain amount of G forces. So different things are sensitive in different ways. Now, especially our brains can't be subjected to more than whatever it is, 4 or 5 Gs or something, and it just turns to mush. So that's really the origin of this whole thing. And it's and then the second part of it, again, is just this confusion about gravity and friction. And, why would something with twice the velocity roll twice as far? And then again, it's such an easy argument to understand that the one distance has to be the same. So the one velocity thing is going to happen to this object. It's going to start going 1v. And you can understand that, okay, well, if 1v is only this distance, then this whole distance, all right, reduced, the other half of the velocity was lost here. So in 3 units of distance, you lost only 1/2 of your velocity, and you lost the other half in this 1/4 of the distance. It's not a hard argument to understand. And the whole idea that gravity is quite obviously a time-dependent force. That's proven by every time you just go through a gravitational field. You have something with gravity over here, and you're going to go through the field of gravity. Obviously, everybody knows the faster you go through the field, the less you're bent. And it's the same as a paint sprayer argument. The faster you go through the paint spray, the less spray hits you. It's obviously gravity is a pushing force, and you're just going through the pushing force more quickly. You'll be exposed to less energy, and you'll be sharing less momentum. All right. So we'll throw that in as some just the extra bits. There's more stuff. I took notes and all that kind of crap, but they have all of the thermodynamics wrong. It's just a fact. They got all these things wrong. I'm using the wrong mouse. That won't work. This one works. All right. So I need to put this back, and I should be able to play it, and we'll see what happens. So all the drama, it's so dramatic, so it's not a conversation about physics, all this show physics, this drama physics, this theater physics. So these are supposed to be people watching this stuff who are, thinking people, and do they really need all of this theater?
By the mid-19th century, scientists and engineers had worked out very precisely how different forms of energy relate to each other.
All right, so there's no different form in any technical way, right? The different forms are really just momentum in smaller and smaller bits. So that's all the form change you can make. You can change something very big, a wrecking ball, and then you can change it into bricks moving, and then little pieces of dust moving, and also sparks and light and all kinds of little pieces fly off. Now all those little pieces have exactly the same momentum, in the sense it's just a mass and a velocity, and that's all there is a mass and a velocity. There's no velocity squared. Law of the lever.
They measured how much of a particular kind of energy is needed to make a certain amount of a different kind.
Right, so it's all the same. So all you can do is say, here's a substance, it takes, like in the case of joule, a certain amount of energy to heat it 1 degree. And then you could say the same thing about expanding something, or, like you could have some metal, and you could say, how much heat does it take to make the metal expand? A certain volume of metal.
Let me give you an example. The amount of energy needed to heat 30 milliliters of water by 1 degree centigrade is the same as the amount of energy needed to lift this 12.5 kilogram weight by 1 meter.
Now that's the tricky one, right? Because we know the amount of energy needed to lift that weight is completely dependent on how fast you lift it. The faster you lift it, the less energy you have to use to lift it. So this was a big, giant mistake they made in trying to do conversions based on moving objects through gravity. Gravity is a constant force, and it's a time-dependent force. It's not the same amount of work no matter what speed you lift at. So it's a lot different, right? So there's huge efficiencies in getting through the gravity quickly, and gigantic efficiencies. And then there's this ideal speed, which is the free fall speed. So at the free fall, if you lift at the free fall speed, that could be a standard, but it has to always be stated lifting at the free fall speed. What the free fall speed would be for the distance you're lifting it.
The deeper point here that people realized was that although mechanical work and heat may seem very different.
Okay, now so that's the part where you're just saying, why would they seem very different? Because in the 1600s, they're already talking about the fact that the energy is in the little pieces inside of something moving about. So they already had the concept of this idea that you fracture something and all the little pieces flying off of the something would add up to the energy that went in. So that was already, an established idea like 200 years before he's saying they started thinking about it. Well, I don't think that's when they started. And the problem is, just like this video, you evade the real subject, which is, why would you bother with this distraction of squaring the velocity? You don't square voltage to make watts. Why would you square velocity? And it's only in these little special cases where there's any indication that there's somehow more energy somewhere because you move something exponentially more energy because you move something quick. And again, something as simple as the 2,000 or 4,000 year old or 10,000 year old lever, the law of that lever tells you it can't be.
They are in fact both facets of the same thing: energy.
Momentum. They're just masses moving. Mass and velocity. That's all there is for matter, is mass and velocity. That's all there is in the universe. There's the force has the power, the movement, and the matter has the mass.
This idea would come to be known as the first law of thermodynamics.
So I don't know what even saying it that way is silly, but just the idea that the energy has to be conserved is the first law, but whatever.
The first law reveals that energy is never created or destroyed. It just changes from one form to another.
Right. One form of what? Kinetic energy or momentum? All right, and I'm clearly advocating there's no good evidence. So again, I'm sorry, any new viewer, I'm sorry. I'm just so frustrated because this is so idiotic. I mean, the simple truth is the demonstration he just did, consistent with his kinetic energy theory, is the same theory that demands that it take 25 times the fuel to spin anything 5 times faster. And we know that isn't real. It doesn't take 25 times the fuel to give something 5 times the velocity. It's idiotic. It doesn't happen. Ever. And yet that's their theory. Just they keep saying it as if it's real, and there's no good evidence of it, and the counter evidence is obvious Schrodinger cat kind of jokes. Are you really dumb enough to think it takes 25 times the fuel to spin a motor 5 times as fast? Are you really that fucking stupid?
19th century scientists realized this meant the total energy of the entire universe is actually fixed.
Right, and Descartes said it in like 1650. All right, so it's not a news flash at all. I don't, So they waste 200 years playing with their little wave nonsense and lose all sense of what motion in the universe really means, which is stuff moving and moving in directions, and then they come back to it again somehow. So again, it's just this, is this honest history of physics? To say that it didn't occur to them until 1850 to figure out that, there's a constant amount of energy in the universe?
Amazingly, there's a set amount of energy that
He just keeps saying it. There's nothing amazing about that idea. There really isn't anything amazing about it. Is there something amazing about saying there's only so much water on planet Earth? There's nothing amazing about saying it. Oh, the water goes from the stream into the ocean and then goes back into the sky and then it falls down again. Oh, it's a cycle. Oh, it's in different forms. Sometimes it's snow. Sometimes it's rain. Sometimes it's just humidity. Oh, I mean, come on. I mean, obviously you can make water, okay, and you can destroy water, but it's a good enough analogy. Is that a big surprise? No. Is that analogy reasonable? Yes. Did people already think that a long time before this guy says it happened? Yeah.
Changes into many different forms. So, in a steam engine, energy isn't created. It's just changed from heat into mechanical work.
Well, we know it's not just magically changed from heat, okay? It's changed from the chemical pressure, okay? The atoms are expanded, all right? Well, you have to argue they're contracted. Sorry, wrong way. So the atoms are in chemical are extracting the energy. So they're taking energy out of the system, all right, out of the chemistry. That creates little pieces, okay, of energy flying off, little bits, radiation. That radiation heats. All right, I should be back. I don't know, some dopey error. Who knows? It's really irritating, computers sometimes. Linux just does little farts like this, just saying, why did you do that? So anyway, I'm back. All right, so he's talking about the energy and the transition. So again, what the key to all these heat engines is pressure. So let's not pretend that it's just heat. It's heat causing some material, like in the case of water, it's a good example, right? Because steam really expands. So the higher you get to a certain temperature, it expands whatever, 500 times. You go 1 degree higher, 10 degrees, 5 degrees higher, and it's double that amount. So that's why steam was used in heating systems, is because you can create a lot of space, okay, pressure, with the steam. Continuing. But let's understand, it's not the heat that is moving the piston. It's the pressure you've created by heating the water that is breaking the water, separating the water, putting energy between the water molecules.
But impressive though the first law is, it begged an enormous question.
So it really is so simple that it's like, what do you mean it begs a question?
What exactly is going on when one form of energy changes into another?
Nothing. It's just smaller and smaller things moving. So that's it. So yes, some of it looks like you can't see it happening, right? We can't see the motion inside of a wire. We can't see the jittering of the silicon wafer as it creates photons. Some of the motion we can't see, but we can understand it's there anyway.
In fact, why does it do it at all?
So it's just exchanges in the real universe is just electrons and protons and the force, okay? So that's the real universe. And all you're saying is the force pushing electrons or not pushing them? If it's not pushing them, then it's free and it's more pressure in the universe. If it's pushing an electron, it's not free. It's moving less than the speed of light now, and therefore there's a little less energy in the outside universe. There's less pressure. So there's more pressure when fewer electrons are moving, and especially back and forth. Because you can sort of understand that back and forth isn't very productive. Jittering is how energy is stored or extracted from the pressure field. And the less jitter there is, that is a neutron star, for example, where everything would be really tightly packed, not doing any jittering.
The answer would in part be found by German scientist Rudolf Clausius, and it would form the basis of what would become known as the second law of thermodynamics.
Rudolf Clausius was a brilliant German physics student.
So it's all this, hyperbole.
From Pomerania, who studied in Berlin and at a ridiculously young age became a very brilliant professor in Berlin and then in Zurich at the new technology university set up there in Switzerland. And in the 1850s and 60s, Clausius offered what is really the first coherent, full-blown mathematical analysis of how thermodynamics work.
So it's not really math because all right, some hours later, I am back. Anyway, computers. So this is somewhere where we left off. I did 40 minutes and it never saved the video. So I gotta do it again and such.
Clausius realized that not only was there a fixed amount of energy in the universe.
Right, so this is something everybody already knew. Lots of people already knew it anyway. That the universe was like anything else, closed system, and you couldn't destroy energy. Come on.
But that the energy seemed to be following a very strict rule. Put simply, energy in the form of heat always moved in one particular direction.
Right, so it's just the same thing as saying pressure only moves in one direction, from high pressure to low pressure. It can't move from low pressure to high pressure. If ever there's an exchange, I have $50, you have $10, we decide to exchange 50-50 what we have. I get poorer, you get richer. Always works that way, yeah. But the point is the universe itself has a mechanism, okay, that restores the previous condition, which is it makes something rich. So basically the sun, the gravity, condenses matter into high pressure again. So it restores the high pressure. So the sun disintegrates, it's low pressure, it is born, it's high pressure.
This insight of his is in fact one of the most important ideas in the whole of science.
So this is just nonsense. I mean, they just make up this crap that this is the most important idea. A really important idea was the fact that mass and velocity is all you needed to know. The whole universe runs on masses moving velocities, and there's no v squared, just like there's no voltage squared. It's silly and stupid and a waste and nonsense. That was the big idea. You blew it.
As Clausius put it, heat cannot of itself pass from a colder to a hotter body.
So again, this was just not very interesting. I mean, everybody had already observed this truth. We don't need it restated.
This is a very intuitive idea.
It's not just intuitive, it's everywhere. There's no examples of the opposite, so it's just not a threat. I don't know what to use for an example. Well, anyway, moving on.
Left alone, this hot mug of tea will always cool down. What this means is that heat will pass from the hot mug, say, to my hand.
Right, and the same thing you could argue is velocity. So you could do the same thing if we could image it with infrared or something. You could see the same thing with rolling a ball down the street or something. You could see it, in the sense that we understand what's happening, that the ball is going to end up losing its momentum, its heat is going to go into the ground. So its momentum in a nice linear one direction is getting converted into angular motion, and that angular motion is ending up banging into the ground, causing a bunch of other stuff to move. So it's just a transfer of motion.
And then again, from my hand to my chest.
So totally unremarkable. Everybody already had done this follow the energy thing. So he does it twice. Like, this is, again, when did you not know this is how it works? It's almost like you can't help but know that's how it works.
This might seem completely obvious.
There you go. That's right. It seems completely obvious. It was completely almost obvious. Lots of people talked about it. Both Leibniz and Descartes understood the universe to be have a conserved quantity. They didn't agree on what the quantity was, but they agreed on the conservation part. You can't destroy the energy. You can just watch it move from one thing to another.
But it was a crucial insight.
It really isn't.
The flow of heat was a one-way process.
So it's not a one-way process if you understand the full universe and understand that gravity is exactly the opposite function, and it's consolidating matter and creating pressure.
That seemed to be built very
creating heat.
Fundamentally into the workings of the entire universe. Of course, objects can get hotter, but you always need to do something to them to make this happen.
You need to expose them to something that has more energy. Yeah, so again, it's unremarkable. You have to add with something richer. You want to make something richer, well, you have to find somebody that has the money and steal it.
Left alone, energy seems to always go from being concentrated to being dispersed.
All right, so that's just nonsense, right? Because we know it goes from being dispersed with gravity to being concentrated. So just so obvious that that's exactly what gravity's doing, taking very dispersed, even the matter itself, very dispersed matter, and consolidating it. Pushing it into each other aggressively.
One of my favorite statements in science was made by the biochemist.
Yeah, douchey bag Professor Atkins. Who the hell is this guy, Peter Atkins? Who the hell is he? Pompous Arrogantus.
Albert St. George, who said that science
who cares what Albert St. George says?
Is all about seeing what everyone else has seen, but thinking what no one else has thought.
So again, there was no extra thought here, except to say something silly like somehow it's a one-way street and all energy dies. Oh, wait a minute. No, it doesn't.
And he, Rudolf Clausius, looked at the everyday world and saw what everyone else had seen, that heat does not flow spontaneously.
All right, so there's no such thing as a spontaneous. So nobody who's at Oxford should think spontaneous is a legitimate word. That's like saying Holy Ghost or something. Just should be forbidden. And every time anybody scientific says it, they ought to just say, oh, let's find a better word, because there's no such thing. Because it's a cause and effect universe. Nothing spontaneous is anything. And the same could be said about random. There's no such thing as random. There's some sort of approximately random, or almost random, or random-like. You can say lots of things, but random, no.
From a cold body to a hot body. It always goes the other way. But he didn't just say, I see that. He actually sat down and thought about it.
Again, and what's the where? What's where? There's not going to be any statement here that it means anything. Nothing came out of this thought that means anything. Entropy is just kind of a silly talk about how something somehow is. It's like saying things get more scattered, and you're going to have a special word for how scattered things get, when you know you can unscatter them. Laser beam light bulb.
Clausius brought together all these ideas about how energy is transferred and put them into mathematical context. It can be
so again, this mathematical crapola. So this is where all the physics, they just broke it all with all this fake math, really. And it is fake. It's a bunch of symbols that don't mean anything. They're not real numbers. It's all kind of just arbitrary mumbo jumbo, and they say it proves something. It doesn't prove anything. It's useful. It's not useful. Who cares? Nobody asks these questions. Answers to questions nobody's asking. All the math you need is, the big M little v equals big V, little m.
Summarized by this equation.
Some more gimmicks. DS, draft science, yay! Divided by draft, whatever the hell that was. What the fuck is that? I guess it's a T, maybe? I don't know. Equal, greater to,
Now,
less than,
was introducing
more
a
than.
new quantity he called entropy. This letter S. Basically, what it's saying in the context of this equation.
Basically what it's saying. It's not a real thing. It's not a substance. Entropy is not a substance. It's not real. It doesn't mean anything.
Is that as heat is transferred from hotter to colder bodies, entropy always increases.
So it doesn't. You know, you could transfer heat from, I don't know, a box to another box of exactly the same size, and nothing's changed. You haven't made more entropy in the universe. You know, you just poured the energy from one thing into another thing. It's just, you know, nonsense.
Entropy seemed to be a measure of how heat dissipates or spreads out.
So it doesn't. So again, we can, I can just keep making the argument, but you don't have to spread the heat. The fact is, though, when we are going to use heat to do work, we, generally speaking, have to pressurize something. We have to expand something and then inevitably contract it.
As hot things cool, their entropy increases.
As hot things cool, their entropy increases.
It appeared to Clausius that in any isolated system, this process would be irreversible.
Except for the fact that there's gravity. I mean, it's just kind of funny. It's just ironic, I guess, that they had already lost sight of gravity as being a real force. And so they didn't even make this simple connection that the radiation coming off of anything, that's what the heat ends up being, is in the smallest bits, force itself, infrared radiation, something moving the speed of light. And that those little bits end up creating pressure in the universe, and that pressure is what's causing gravity.
Clausius was so confident about his mathematics that he figured out that this irreversible process was going on out there in the wider cosmos.
Cosmos. So again, and obviously there's no way to make the gravitational argument into one where somehow you're dispersing or spreading or making more chaotic or any of that, when it's doing exactly the opposite.
Speculated that the entropy of the entire universe had to be increasing towards a maximum, and that there was nothing we could do to avoid this.
So this is just wrong, and so, like I said, every star you see in the sky is proving the opposite.
Idea became known as the second law of thermodynamics, and it turned out to be stranger and more beautiful,
So why this talk? Strange and beautiful. This is all such baby talk, mushy stuff. This is something religious kooks will say or something. I mean, why is this in science, talking about beautiful? It's just pathetic. It's not. It's not scientific language.
universal than anything Clausius could have imagined.
So all this playing of pianos to say energy moves from hot things to cold things. Pressure moves from high pressure to low pressure. Wow.
The second law of thermodynamics seemed to say that all things that gave off heat were in some way connected together.
So why this? You're saying, what does this have to do with anything? So Alpha Centauri is giving off heat. It's a sun. It's not connected to our sun in any way. There's no connections. It's just nonsense. I mean, that's the religion part, right? They're always trying to make everything spiritual or something. There's no connection beyond the fact that photons fly off of stars and travel billions of light years and hit us. So what? Our light hits them. We're not connected in any other way.
All things that gave off heat were part of an irreversible process.
So again, more nonsense. Irreversible process when the process is reversed by the very creation of suns.
That was happening everywhere. A process of spreading out and dispersing.
So it's easy to break things. It's easy to, cause things to fall apart, and it's harder to put things together. Now that's sort of a truth, but the fact is that we can choose light bulb or laser beam.
A process of increasing entropy. It seemed that somehow the universe shared the same fate as a cup of tea.
So again, it doesn't. So the universe isn't sitting here just dispersing energy and it disappears and that's the end of the universe. It goes away somewhere. So again, the very fact is, the very fact that you can see that cup is the infrared radiation. It's spewing force at the speed of light. And what is that force going to do? It's going to hit other objects and push electrons and protons.
The wonderful thing about the Victorian scientists is that they could make these great leaps and that they could see that...
So it wasn't a great leap. They thought about it for hundreds of years. They talked about it for hundreds of years. So it's just a huge lie to say people like Galileo, Descartes, and Newton weren't already talking about this kind of stuff, because they were.
Their study of thermometer in a beaker actually could be extrapolated, could be enlarged to encompass the whole universe.
Nonsense. It just, again, I don't even know why they do this when it's so obvious that the creation of the stuff we see in the universe, right? The big giant stuff, the creation of that big giant stuff is the process that is the opposite of the cup getting cold. That stuff getting hot. I don't know, hours and hours of la la woo 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 music.
Despite the successes of thermodynamics,
So what successes? So again, more talk about some kind of success. Somehow knowing the universe is running out of energy was critical to the invention of the tea bag. No, it wasn't.
in the middle of the 19th century, there was great debate and confusion about the subject. What exactly was this strange thing called entropy?
So let's just understand the context. He's talking about matter and energy. He fudged the whole subject of dealing with the duality between momentum and kinetic energy. He talked about Leibniz, and that's the key moment when they confused something obvious and simple and turned it into something wrong and stupid.
Why was it always increasing? Answering this question would take an incredible intellectual leap.
It's just silly.
But it would end up revealing the truth about energy.
So it doesn't reveal anything, doesn't say anything. It's just the fact that there's little tiny stuff in the universe and there's big stuff. And the fact is that the tendency is for stuff to move from the big things to the small things, but it's just a tendency. It's not a law.
And the many forms of...
There's more little stuff than big stuff, you could argue. But look, there's only one real universe, and the real universe only has electrons and protons in it, frankly, and force. And there's no entropy of any kind.
Order and disorder we see in the universe around us.
So again, more nonsense. So he says there's order and disorder, and your claim is that it only moves in one direction, disorder. So where's the order coming from?
Many scientists would tackle the mysterious concept of entropy, but one more than any other would shed light.
Hold on. Alright, should be back. Maybe I'll save this while I got a chance, just in case. Alright, that looks like it went alright, so continuing.
On the truth. He'd show what entropy really was, and why, over time, it always must increase. His name was Ludwig Boltzmann.
So again, it's not true. So they're giving all this credit to somebody who proved something that's just not true. It doesn't always go.
He was one of science's true revolutionaries.
So it's only a revolutionary in the sense that he's, a fine Catholic, because he believes the crap they believe. And he argues for the crap they believe, and that's it. But the truth is, he was wrong-headed and wrong-tracked. All this. So if they ever make a statue of me, I hope it's a lot better than this.
Boltzmann had been born in Vienna in 1844. It was a world of scientific and cultural certainty. But Boltzmann took little notice of the entrenched beliefs of his contemporaries.
So none of this is true. So in the late 1800s, nothing was entrenched. It was all kinds of arguments about waves and particles and all kinds of shit. So bullshit, bullshit, bullshit.
To him, the physical world was something best explored with an open mind.
And so there's absolutely no evidence of any of that being at all interested to physicists. They have no open mind. They don't. They certainly don't care about anything like evidence and logic and consistency or any of those kind of notions. Careful, not even. It's not even a word they understand at all. Caution.
Boltzmann wasn't your stereotypical scientist.
And whatever the stereotypical is, what's the stereotypical? Big giant douche. Yeah, right.
In fact, he had the kind of temperament that most people might associate with great artists. He was ruthless.
Are shitty artists, right? I mean, so it's the big joke, right? I mean, there's just as many neurotic great artists as there are neurotic shitty artists. And likewise for physicists.
Logical and analytical, yes. But while working, he'd go through periods of intense emotion. And these would be followed by terrible depressions, which would leave him completely unable to think clearly.
Whatever. So I've been there and done that, sort of. I don't know about the emotion part, but, the horror and terror, I've had some of that.
He had terrible sort of mental crises and breakdowns in which he really thought that the world was coming apart at the seams.
Boy, he should live now. Yeah. Ooh. You want to see something just ready to fall apart. I mean, it's just full-blown idiocracy. It's just so ironic. All this technology, all this good stuff, and it's all just pissed away.
And yet, these were also accompanied by some of the most profound insights into the nature of our world.
And what's the insight? Sorry, there is none. Okay. Look, I'm not going to say that. Atomic theory, understanding that matter is made out of something smaller. But again, that is not a new idea. We didn't need Boltzmann to figure that out.
Outside of mathematics, Boltzmann was passionate about music and was captivated by the grand and dramatic operas of Wagner and the raw emotion of Beethoven.
Who cares? Who cares?
He was a
Who cares? Who cares?
and could lose
Who
himself for
cares?
hours in the works of his favourite composers, just as he could lose himself in deep mathematical theories.
Like what? Yeah. So again, all this talk about math, big M little v equals big V little m. There, we're all done with the math.
Boltzmann was a scientist guided by his emotions and instincts, and also by his belief in the ability of mathematics to unlock the secrets of nature. It was these traits that would lead him to become one of the champions of a shocking and
So it really is kind of ridiculous just to think that the model of it moving is not going to be mathematics. A duck's organs, where its liver is, where its kidneys are, and it's not mathematics. Mathematics isn't going to make you understand why evolution did this or why evolution did that. It's just crap.
controversial new theory, one that would describe reality at the very smallest scales, far smaller than anything we could see with the naked eye. During the second half of the 19th century, a small group of scientists began speculating that at the smallest scales, the universe might operate very differently to our everyday experiences.
And the ironic truth is, no, it doesn't. It's the same thing. It's mass and velocity, and that's all there is. That's all that's happening to electrons and protons. They're just throwing force at each other. They're getting knocked by it, and that's it. There's nothing else going on.
If you could look close enough, it seemed possible that the universe might be made of tiny, hard particles in constant motion.
And the fact is, they're not in constant motion. So obviously you could argue the force could be described as that, but it isn't hard in the sense that they stick to matter in the right circumstances and push it. Okay, and then the matter, we know, well, the atoms aren't hard. Okay, we know that the electrons and the protons are the only thing that are really playing. They're the ones, they're dancing about. They're jiggling is all that creates structure and shape. You only have a hard surface because there's electrons all constantly pushing out. Pushing back.
Viewed in terms of atoms, heat would suddenly become a much less mysterious concept. Boltzmann and others saw that if
So heat wouldn't be just round balls, okay? We know that the atom is electrons and protons. The electrons and protons have to be arranged where they can balance each other's pressure, that the atoms are actually sharing their electron pressure. So if I change the pressure on one atom, I change the pressure in all the other atoms. It's much more complicated than just jiggling balls. Well, it's not even that it's complicated. It's just there's a go smaller view that's more accurate. This isn't really accurate because atoms aren't balls.
If an object was hot, it simply meant that its atoms were moving about more rapidly.
And it's usually the electrons on the outside of the atom that are doing the moving, not the nucleuses.
Viewing the world as atoms seemed to be an immensely powerful idea.
And a really old one. So again, this isn't news. So there were lots and lots of physicists over the whatever 300-year period that sat there and talked about, stuff being made out of smaller bits, elements. I mean, look at, Newton knew that.
But this picture of the universe had one seemingly insurmountable problem. How could trillions and trillions of atoms, even in a tiny volume of gas, ever be studied? How could we come up with mathematical equations to describe all of this?